Welcome to ALP Chemistry on Video. This is a live recording, and in class today Scott is with us, and today's lesson is on Chapter 12, Part 2 on molecular shape. So by this point you've already had the lesson on Lewis structures, so now we're going to continue and do molecular shape, which is based on VSEPR theory. So we've got to go find the right page. Not quite there. Let's see. Should be close to there. Should be this one. There we are. Molecular shape, which, as I said, is based on VSEPR theory. VSEPR is how we pronounce VSEPR. And VSEPR stands for valence shell electron pair repulsion, which is a mouthful, but the concept is fairly simple. Before I tell you about it, just remember that Lewis structures don't show shape. Lewis structures are generally flat, and the bond angles are all 90 degrees to one another. The reality is that molecules aren't flat and their bond angles aren't 9 degrees to each other. What happens is that the electron pairs repel each other. So that's what the name says, that the valence shell, and in this course I've been calling them orbitals. The shell is the older model of electron structure. So we're dealing with the valence orbital electrons, and the theory is that the pairs repel each other, and they try to get as far apart from each other as they possibly can. So which is what I say here. And what that means is that when the electron pairs try and get as far apart as they can, they maximize their bond angles. So they have the largest bond angles possible. And that includes both the bonding pairs and the lone pairs. So it's not just the bonds. We have to take into consideration the lone pairs as well. So the molecular shape, when we talk molecular shape, we're talking about where the atoms are. Specifically, but we may need to know where the electrons are to figure out where the atoms are. So when we do the shape, we're going to have to be thinking about all the electron pairs, including the lone pairs, but when we name the shape, we're naming it just for where the atoms are. So we'll see that in a little bit. So the first example is BEF2, and to illustrate this, I like you to picture as if your fists are fluorines and your head is beryllium and your arms are the bonds. So if you stick your arms straight out and then imagine that your arms are going to repel each other, so they're going to spread apart and spread apart and spread apart until they're as far apart from each other as you can possibly get, which will be straight out to your sides. If you keep going behind your back, then your arms are actually starting to get closer to each other again, and they'll kind of spring back to the point where they're straight apart from each other with your arms spread out completely. If you were to go up, same thing, your arms are going to get closer together, and because they repel each other, they'll spring down again into a position where they're 180 degrees or as far apart as they can possibly get. And in fact, what happens with real molecules is that the bonds actually do spring a bit. So they may get a little closer, and then they'll spring apart and actually vibrate a bit. So they'll go up and down or back and forth, and the bonds actually vibrate. And the energy which causes them to do that is infrared. So the energy transitions which cause bond vibrations in molecules are infrared energy. So that's the energy that your typically TV remotes use infrared. So there's enough energy there to start bonds vibrating. So if you have two electron pairs, they will adopt a linear arrangement. So they're in a straight line. And it turns out that if you don't have lone pairs, then the electron arrangement will be the same as the shape. So the molecular shape is also linear. And that's because all the atoms are in a straight line. So we can draw a straight line through all the atoms showing that they're linear. And remember, molecular shape says where the atoms are, not necessarily where the electrons are. When we're trying to figure out the shape, we need to look at the central atom in a molecule. So in this case, it would be the beryllium. So we're looking at how many electron pairs are around the central atom. In that case, there are 2. So if you have 2 pairs around a central atom, the arrangement will be linear. If you have 3 pairs, it will, as we've shown in this Lewis structure for BF3, if you have 3 pairs, and here is the Lewis structure where I'm showing all the bond angles are at 9 degrees. In fact, the arrangement which gets the electron pairs in the bonds as far from each other as possible is what's called a planar triangle arrangement, in which the bond angles are 120 degrees to each other. So 3 electron pairs adopt a planar triangle arrangement, and we call the molecular shape a planar triangle or a trigonal planar, and either name works. Either name is okay. And just take note that when we say planar, it's planar, A-N-A-R, as opposed to A-N-E-R, in which case you'd be talking about a tool that you use to trim wood down. That would be a planar. Now, if you have 4 bonds, and again I've shown the Lewis structure here for CH4, and in the Lewis structure all the bonds are at 9 degrees to each other. But remember, the Lewis structure isn't showing the shape. The shape actually is in 3 dimensions, which is hard to draw on a flat surface like the smartboard or on paper. What I'll do is I'll show you a model, so you can see the 3-dimensional model. So I'll just pause the video for a moment, and if you're watching on video, make sure you have the model in front of you. I now have a model kit in front of me, so if you're watching on video, you might need to ask the instructor for the model kit and ask the instructor to build a tetrahedral model for you so that you can see what it looks like. So this is in 3 dimensions. Now, the linear and the planar triangle are easy to draw on paper or on the smartboard, but a tetrahedral, because it's in 3 dimensions, it's a little hard to draw. And there is a convention for drawing it, and the convention is that things that are in the plane you draw with solid lines, things that are behind the plane use a dashed line, and things that are coming out of the plane towards you use a wedge. So I'm holding the model now with 2 of the atoms and the bonds in the plane of the paper, aligned with the plane of the paper. And I'm holding the hydrogen that is behind the paper, and then there's another hydrogen coming out of the paper towards you. And the way that's drawn on paper is 2 solids, a wedge, and a dashed. The solids are in the plane of the paper, the wedge is coming out towards you, the dashed is going away from you. And so whenever you draw a tetrahedral, you draw it that way. 2 solids, a wedge, and a dashed. And that will represent a tetrahedral. So 4 electron pairs adopt a tetrahedral arrangement. And the molecular shape is tetrahedral. Okay, so that's CH4. Now let's do some with lone pairs. So the molecular shapes we've done so far, there were no lone pairs. Now when you've got lone pairs, the electron arrangement and the molecular shape will actually be different. So we have here NH3 with its Lewis structure, and you see that we have 3 bonding pairs and 1 lone pair. That's 4 pairs total. And 4 pairs will arrange themselves in a tetrahedral. That's the arrangement which gets them as far apart from each other as they possibly can. So we can draw that like this, where again, drawing a tetrahedral, we have 2 solids, a wedged and a dashed. Now we have the 3 hydrogens at 3 ends, and then we have a lone pair at the other end. So at one head of the tetrahedral, we have the lone pair, as I've shown here. So the electrons are still in a tetrahedral arrangement because you have 4 pairs of electrons total, and the arrangement which gets them as far apart from each other as they can get is tetrahedral. But the molecular shape, which is talking about where the atoms is not a tetrahedral. If we cover up the lone pair, it looks like a pyramid. And that's why the molecular shape is called a triangular pyramid, or a trigonal pyramid. And the reason why it is written as a triangular pyramid and not just a pyramid is that you can have pyramids that have the bottoms on them are different shapes other than triangular. And for example, the pyramids of Egypt are square pyramids because the bottom is a square. So this is a triangular pyramid. So if you were to look at the bottom of it, it would look like a triangle. So to show the model of this, what we do is take a tetrahedral, and if we pull the top off so that all you have left on top is the little stem which you would stick the straw onto, the little black stem represents the lone pair. And you can see the 3 hydrogens around, and you see it looks like a pyramid. So that's why the name triangular pyramid. For water, we have 2 lone pairs now. So if you count the pairs total, there are still 4 pairs because you have 2 bonding pairs and 2 lone pairs. So there are still 4 pairs total. And the Lewis structure, the way we draw this Lewis structure, the first Lewis structure looks as if it should be linear. But remember, the Lewis structure doesn't show shape, and it doesn't really matter where we put the bonds. In the second drawing here, we show the bonds at a right angle. And that's perfectly fine for a Lewis structure. The Lewis structure isn't showing shape, it's just showing what atoms are connected to what and where the electrons are. To draw the shape, what we need to do is to draw a tetrahedral, because there are still 4 pairs total, and 4 pairs, to get as far apart from each other as they possibly can get, will arrange themselves into a tetrahedral. However, the atoms, although the electrons are in a tetrahedral, the atoms aren't. The atoms are in a V. And to represent that using the model, we would take a tetrahedral, and this time we pull 2 pieces off a tetrahedral. And you'll see that you have a black atom with 2 stems sticking out of it, and 2 atoms, and it's now in a V shape. So to draw this V shape, what you would have is you would have a tetrahedral where 2 parts of the tetrahedral are the lone pairs. When you draw the shape, you don't have to draw the lone pairs in. So when you're drawing it, you can just draw the oxygen and the 2 hydrogens in a V and just cover up the, just erase or cover up the lone pairs. So you don't have to show the lone pairs in a when you're drawing the shape. If you did, I wouldn't mark it wrong. That would be okay. But you don't need to. And I've shown 2 different perspectives of water here. One where they've both got 2 solids, a wedged and a dashed. But in one of the pictures I have the hydrogens on the solids, and in the other one I have the hydrogens on the wedged and the dashed. Most of the time it's drawn in the first way with the hydrogens on the solids. So in this case, the arrangement of the electron pairs is still tetrahedral because you still have 4 pairs total. But the molecular shape is called a V shape, or bent. And bent because it's bent from linear into a V shape. So now let's put all this information that we've talked about into a summary table. And we'll blow it up full screen. So here's the summary table. And what we're showing in the first column is the total number of pairs. And the first three shapes, we don't have any lone pairs. And when we don't have any lone pairs, the electron arrangement and the molecular shape is the same. When we do have lone pairs, the electron arrangement and the shape will be different. So there are basically 5 shapes to memorize. Well, 5 or 6. 3 of them are based on a tetrahedral and just having different numbers of lone pairs. So the first is having 2 pairs and no lone pairs, and both the electron arrangement and the shape are linear. If you have 3 electron pairs, no lone pairs, both the electron arrangement and the shape will be a planar triangle. 4 lone pairs, no lone pairs, tetrahedral and tetrahedral. When you have 4 lone pairs, but now you have 4 pairs total, now you have 1 lone pair, the electrons are in a tetrahedral, but the atoms will be in a trigonal pyramid shape. If you have 4 pairs total and 2 lone pairs, the electrons will still be tetrahedral because you still have 4 pairs total, but the atoms are in a V shape. And finally, if you have 4 pairs total, but 3 of those are lone pairs, because you have 4 pairs total, the electrons are still tetrahedral, but now you only have 2 atoms because 3 of the lone pairs are 3 of the pairs are lone pairs. That leaves you only 1 pair to bond with. You only have 2 atoms, and 2 atoms can't be anything but linear. So that will be linear. So let's do some practice examples. So we've got CH4, and how many pairs total do we have? 4. We have 4 pairs total and no lone pairs. So if you go back and look in the table, if you need to refer to the table, you see it's tetrahedral. And the way to draw that is to draw that with 2 solids at an angle, a wedge, which represents the bond coming towards you, and a dashed or dotted to represent the bond going away from you. And that's how you would draw that. So that's CH4. HBr, if you look at Br, there are 4 pairs around Br, but 3 of those are lone pairs. So if you have 4 pairs, the electron arrangement is what? Right, it's tetrahedral. But you only have 2 atoms, so the shape can only be linear. In terms of drawing this, you can draw it this way. Here I put a little check mark to show that this is okay. When you draw the shape, you don't have to show the lone pairs. You can, but you don't have to. In this case, the Lewis structure and the molecular shape are the same because it's linear. So you can draw it this way without showing the lone pairs. You can even draw it this way if you wanted to show where the lone pairs are in 3 dimensions. That would be okay too. So you can draw it as a tetrahedral around bromine with 3 lone pairs at 3 heads of the tetrahedral and hydrogen at the other head. So that would be okay. Now water. Water, we have 4 pairs around the oxygen, so the electrons are in what arrangement? Right, 4 pairs is always tetrahedral. And the shape is what? V-shape or bent. Right, is V-shape or bent. And if you weren't sure, initially while you're getting used to doing these, if you can't remember, you might have to have that table in front of you to refer to. So you'd go and look and say, well, we have 4 pairs total, and 2 of those are lone pairs. So then you'd go look in your table. You'd see 4 pairs total and 2 lone pairs is a V-shape. So that's how you do that. And to draw the V-shape, you can draw an oxygen with the two hydrogens at an angle. Or if you want, you can draw it as the tetrahedral, showing all the electron pairs and just having the lone pairs at two heads of the tetrahedral. If you have a structure where there are multiple bonds, like double or triple bonds, for the purposes of shape, consider them to be singles. So if we look at carbon dioxide, CO2, which has this Lewis structure, you see there are two double bonds, you would kind of look at the carbon and you would say, well, carbon's got 4 pairs around it. Well, the double bonds are one bond. Even though it's a double bond, it's considered to be one bond for the purposes of shape. So if you look at this structure, you would say there are 2 pairs around carbon. And the shape that's associated with 2 pairs and no lone pairs is a linear. So you would say the shape of this is linear. And in fact, if you look at where the atoms are in this, the atoms are in a straight line, which is what linear means, line ER. So the atoms really are linear. So it is a linear structure. And I think I can illustrate that with a model. So I should have a carbon in the middle. So I'll use a black for the carbon, and maybe I'll use blue for the oxygen. And so I've double bonded a blue to the black carbon, and now I'm going to attach a second blue with the double bond. And the model shows that it is, in fact, linear. All the atoms are in a line. So that's what carbon dioxide looks like as a model. And if you're watching this in video, ask the instructor to build a model for you of carbon dioxide so that you can see for yourself. Okay, let's look at this structure here. And I've given the Lewis structure. And I've actually drawn it as the shape. But let's name the shape. So looking at one of the carbons, both carbons are the same. So in terms of the number of things which are bonded to it. So we take one of the carbons, and how many pairs do you count around the carbon if you consider that the double bond is considered a single? 3. And 3 pairs is a what? 3 pairs and no lone pairs? Is a planar triangle, right. So 3 pairs, no lone pairs is a planar triangle. So it's a planar triangle around each carbon. Now there's something interesting that happens with these structures. These structures, because they're flat, you can have things sort of on the same side or on opposite sides of the double bond. So I'll represent that by having 2 black pieces in the models bonded together with a double bond, and 2 white pieces representing hydrogens and 2 reds representing chlorines. And there's 2 arrangements you can have with this. You can have the chlorines. So what you would do with the structure is you would take 2 hydrogens and replace them with chlorines. And there are chemical ways for doing that. There are some chemical reactions that can be done by. You can end up with chlorines on the same side of the double bond. And chemists need a way to name these because these actually are different structures. You can get chlorines on the same side of the double bond, or you can get chlorines on opposite sides of the double bond. And when they name these compounds, if they're on the same side of the double bond, they call them cis. And if they're on opposite sides of the double bond, they call them trans. So all this to set up a chemistry joke. So if you have TER on the same side of a double bond, and TER doesn't mean anything, it's just something for the joke, what would you have? You'd have sisters. So that would be cis. Because they're on the same side of the double bond. So that's sisters. The one down below, a lot of people don't get this joke anymore. This one, you have a sister and another sister, but they're on opposite sides of a double bond.
Transistors.
So they're transistors, right? Transistors. However, I've told that joke to a few classes now, and people don't know what a transistor is anymore. So they just kind of look at me with a blank look and go, "What's a transistor?" So a transistor is an electronic component, and these days, now that everything's digital, people don't think about transistors anymore. But back in the 60s and the 70s, people had transistor radios, and it was a really cool thing to be able to take a radio, because it used to be a radio was this big thing that you'd have in your living room, and it was this big device which might be 3 feet tall, and that was a radio. And in the 60s, when people could actually carry a radio in their hand, it was kind of the first portable electronic device, and it was made possible because of the transistor. And so everyone knew what a transistor was, but people now don't know so much what a transistor is. So I tell this joke now, and people kind of look at me, a blank look, and what are you talking about? Okay, so that's it for molecular shape. The next topic is polarity, which relates to molecular shape. And in the course so far, you've already learned that bonds can be polar. And what makes a bond polar is if you have two atoms with different electronegativities. So if you were to look up the electronegativities in the periodic table for both carbon and oxygen, you would find that oxygen has a higher electronegativity than carbon. What that means is that the electrons will be attracted to the oxygen more than to the carbon, which will make the bond polar. So I've represented this as an arrow. The arrow is called a dipole moment, and it represents the movement of electrons toward the oxygen. I've also got a little squiggly with a plus sign below the carbon and a little squiggly with a negative sign below the oxygen. The little squiggly symbol is a delta. And in science, the Greek letter delta means difference or change. And often it's represented by a big delta. A capital delta, it looks like a little triangle. But here, because the electrons are not completely transferred from the carbon to the oxygen, they're only slightly moved over, we use a little delta to indicate that it's a small change. So the carbon is slightly positive, the oxygen is slightly negative. So a bond can be polar, but that doesn't necessarily mean the whole molecule will be polar. Not all molecules containing a polar bond are polar. But if a molecule is polar, what that will mean is that the electrons aren't evenly distributed. They're closer to one side of the molecule. So what makes a molecule polar? There are two things you need for a molecule to be polar. It has to have polar bonds, and it has to have an asymmetric shape. Now what I mean by asymmetric shape, symmetry is the ability of things to look similar to each other when you do an operation on them. So an operation would be like a reflection or a rotation. So if you take your hands and you line your hands up so that their palms are facing each other, your hands have mirror symmetry, what's called mirror symmetry, because you can line them up and they look like, and they'll fit right over top of each other. They'll match if their palms are facing each other. So they have mirror symmetry, but they don't have rotational symmetry, because if you line up your hands that way and then you rotate them 180 degrees and now you try and line your hands up, they don't line up anymore. So your hands have mirror symmetry, but they don't have rotational symmetry. What we're talking about when we're talking about symmetry here is usually rotational symmetry. So if you can, and when I mean symmetry, what I mean is if you can rotate a molecule in such a way that the atoms change positions and you can't tell that it had been rotated, then it has symmetry. It's asymmetric, it doesn't have symmetry. If you were able to rotate the molecule, the atoms all change positions, and you could tell it had changed, then it's asymmetric. So the test that I use to test for symmetry is if you were to close your eyes and someone came along and rotated it such that all the atoms changed positions, and then you opened your eyes again and you can tell it had been rotated, then it's asymmetric. And if it's asymmetrical, it will be polar. So let's illustrate that with the next few examples. So let's look at O2, oxygen. an oxygen molecule. Oxygen has the same atom on either side of the bond, so neither atom can pull the electrons off the other because they have the same electronegativity. Because the bond isn't polar, that means the first thing you need to make a polar molecule isn't there. So you have no polar bond, and because you have no polar bond, the oxygen molecule is non-polar. For carbon dioxide, CO2, we do have polar bonds because there is a difference in electronegativity between carbon and oxygen. The bonds are polar, and we can represent that by showing arrows going from the carbon towards the two oxygens. And we can also represent that with a little negative on each oxygen and a little positive on the carbon. And the arrows are representing the dipole moments. But in this case, the dipole moments cancel each other out because you have one dipole moment going in one direction. You have exactly the same quantity of dipole moment going the other direction, and it's like a tug of war. They cancel out. So that's what happens when a molecule is symmetric. So this molecule has polar bonds, but it's symmetric. It's symmetric because if we were to rotate it and exchange positions with the oxygens, which I'll show with the model, you can't tell it had been rotated. And if a molecule is symmetric, the dipole moments will cancel out. So this molecule is symmetric. It is not asymmetric. Because it's symmetric, it's nonpolar. If we look at the water molecule down below, you have oxygen with an electronegativity of 3.44 and hydrogen with an electronegativity of 2.20. So you have the electrons attracted from the hydrogens toward the oxygen. So you have two dipole moments, but in this case the molecule is not symmetric. So if I represent it using the model and I were to hold it and rotate it such that the bonds change position with the lone pairs, so when I talk about rotating, I include the lone pairs in terms of the rotation. You can tell it's been rotated by changing positions with the bonds and the lone pairs. You can tell it's been rotated. So it is asymmetric. So as I said here, it has polar bonds and it's asymmetric. And because it's asymmetric, the dipole moments don't cancel out. And that's what I've attempted to draw with this drawing here. I've taken the dipole moment, so I took this dipole moment here as the top arrow, and this dipole moment here as the arrow going down. And when I add them up, I get this red arrow, which I call a net dipole. And if you have a net dipole, the molecule is polar. So water is a polar molecule. However, if water was linear, it's not, it's a V-shape, but if water was linear, the dipole moments would line up like this, and they would cancel out because they'd line up exactly opposite each other. So if H2O was linear, it would be nonpolar. But it's not. Because it's a V-shape and it's asymmetric, it's polar. So let's look at some examples. This is carbon tetrachloride. It has polar bonds, but it's symmetric. I show the polar bonds as dipole moments going from the carbons to the chlorines, from the carbon to the chlorines. But it's symmetric. And a tetrahedral with the same thing on the end of the tetrahedral will always be symmetric. And because it's symmetric, it's what? Polar or nonpolar? It's nonpolar. Okay, here's the so what. So big deal. We can look at the shape of a molecule. We can decide whether it's polar or nonpolar. Why do we care? So here's why is polarity important. And the reason it's important is what's called the like versus like rule. And that rule is that polar compounds will tend to dissolve in polar solvents. nonpolar compounds will tend to dissolve in nonpolar solvents. However, nonpolar compounds don't like to dissolve well in polar solvents and vice versa. Polar compounds don't like to dissolve in nonpolar solvents. So for example, water is polar and is very commonly used as a solvent for covalent compounds. So if we're talking about water, let's think about CO2, carbon dioxide. And we've already said that this is a nonpolar molecule. So how soluble do you expect carbon dioxide to be? It's nonpolar, so we don't expect it would be very soluble in water. So in your experience, do you find that? Do you think carbon dioxide is soluble in water or not? Why not? What happens when you shake a bottle of pop? It fizzes. It fizzes because the carbon dioxide comes out. So the carbon dioxide dissolved in the water, which is mainly what soda pop is, mainly water, the carbon dioxide doesn't want to stay in there. You can force it in there if you put high pressure on it, but if you agitate it and give it a chance to come out, the carbon dioxide will come out. So if carbon dioxide was polar, it would be soluble in water, and when you shook up your bottle of pop, the carbon dioxide wouldn't come out again. So there's an example. A couple of other examples. We looked at carbon tetrachloride. We found it was nonpolar. And in fact, the reality is it isn't very soluble in water. If you put carbon tetrachloride and water together, you'll get a layer of carbon tetrachloride, one layer of carbon tetrachloride, one layer of water. And in fact, this compound is used to do chemical separations with water. Because it's nonpolar, if you have very small amounts of nonpolar molecules dissolved in water, you can actually extract them with carbon tetrachloride, because what will happen is that the nonpolar compounds will go into the carbon tetrachloride layer and from the water layer. And then you can drain off the carbon tetrachloride layer, and then you can analyze those compounds in the carbon tetrachloride. If we were to take two of the chlorines off of carbon tetrachloride and replace them with hydrogens, all of a sudden that molecule isn't symmetric anymore. And now if we were to rotate it such that we were to rotate it, say grab the top chlorine and rotate it such that this chlorine on the right went in place of the hydrogen there, and this hydrogen here rotated around to where the chlorine is, you could tell it had been rotated. So if I try to build the model of that here, then I can show. So I've got two hydrogens sticking out of a black piece, and then I'm also going to stick two red pieces on to represent the chlorines. And then if I were to rotate this such that all the atoms change positions, then you can tell it's been rotated. So it's asymmetric. Because it's asymmetric, it's polar, and because it's polar, it's soluble in water. And in fact, these compounds are kind of concern, because if you chlorinate water, if the water's got a lot of carbon-containing compounds in it, you can actually make some of these. And because they're soluble in water, they'll stay in there, and people are concerned about them. They're not easy to separate out because they're soluble, and people are concerned about the health effects of these things. Which leads me to another chemistry joke, and the chemistry joke is, why did the white bear dissolve in water? Right, because it was a polar bear. You got it. Okay, and here's another application. The other application of this idea of polarity is soap and detergent and washing things. So the purpose of soap and detergent is to get nonpolar compounds that normally would not dissolve in water to dissolve in water so that you can rinse them off. And how does it work? Well, soap and detergent molecules have a polar end and a nonpolar end. The polar end will dissolve in water, and the nonpolar end will dissolve in your nonpolar dirt and then carry it into water solution. And then you can rinse it off. And when you wash something, you really should rinse with water. A lot of people, when they wash the dishes, they don't rinse with water. They just soap them up and then stick them in the drying rack. Well, if you don't rinse with water, then you have a film of soap and dirt still left in your dishes. So the purpose of the soap is to get the stuff dissolved so that you can rinse it off. So you really should rinse it off to get your dishes properly cleaned. In a chemistry lab, when someone is cleaning, they really need to think about what their dirt is. And in this sense, dirt is kind of a relative term because dirt really is anything you don't want in your glassware or your containers. And in fact, water could be dirt. There are some chemical reactions which are sensitive to water, and if you're trying to do one of those reactions, water could interfere, and it might be that you want to get the water out of your containers before you do the reaction. So in that sense, water could be dirt. Normally you wouldn't call it dirt, you might call it contamination. But there are procedures for getting water out of your containers. So you would want to think about what your dirt is. So for example, if you're working with something which is soluble in water, let's say you're working with sodium chloride, table salt, and you know it's soluble in water, if that was the only chemical you're working with in a particular piece of glassware, all you need to clean it out is just some clean, pure water. So you could use some deionized water, which has had all the ions taken out of it, or distilled water, which has distilled and removed both the ions and the organic material out of it. So all you need is some deionized or distilled water. Just rinse your glassware. That will rinse the salt out because it readily dissolves in water. In some cases, you can make things worse by adding soap or detergent, because soap and detergent may have all sorts of other things in it as well. So you may have some glassware which is clean, except for maybe one compound like sodium chloride, but then when you put soap in it, soap might have copper ions, it might have calcium ions in it, it might have sodium in it. It's probably got all kinds of different ions in it. So by using the soap, you might make things worse. The lesson is don't use soap unless you really need it. If you need to clean something that's non-polar out, then you can use soap. Otherwise, if it's something that's soluble in water, just use some pure water to rinse it out. So you might need to think about what it is you're cleaning before you clean it out. And if you're trying to clean out something that's non-polar, typically we would use soap to dissolve it first, rinse it out with tap water. The tap water will carry out the soap and the non-polar compounds, and then usually would finish with deionized or distilled water to make sure that the rest of those ions are cleaned out. And that's it for the lesson on shapes. So we have a few examples. You can work those out on your own. The next step would be to do the worksheet. So you may have already done the Lewis structures on the left side of the worksheet. The next thing for you to do is to do the shape on the right side of the sheet. So you will draw the shape, name the shape, and tell me whether it's polar or not. And that's it for that lesson.